In this video, we're going to be talking about optimization, which is one of the applications of derivatives, of differential calculus in real-world settings. Okay, so what's the objective? The objective is to use differentiation to solve a variety of optimization problems in mathematics, physics, economics, or business. So let me go ahead and give you the strategy for optimizing problems. Okay, so you got to read the problem, draw a picture if necessary, state the two formulas required, and usually what you do is you're going to need a multitude of formulas, and you might need one, two, or three. Solve one equation and substitute into the other to have a function of a single variable. Take the derivative, solve for the critical points, and test them. That's it. So basically, we're just taking two equations and solving for one, putting it in the other, taking the derivative to get the critical points. And those critical points are going to be the ones that help me optimize my problem. All right? So let's go ahead and look at some examples. Number one. Let's read it. It says read the problem. So two numbers add up to 30. Find the maximum area of these two numbers. Now, what you need to understand is I'm going to add up two numbers to get 30. So I can say something like 20 plus 10. What's 20 plus 10? Well, 20 plus 10 is 30. I could say, oh, what about 5 plus 25? 5 plus 25 is equal to 30. So the sum of these two numbers is equal to 30. Now, what they want is they want to find the maximum area of these two numbers. So in this scenario, I'm going to take 200 and I'm going to multiply it by 10. And that is going to give me an area of 2,000. What about the other one? Let's pretend I have 5 times 25. That's going to give me 125. So what are you noticing about this scenario? Well, oops, I made a mistake here. I put 200. It's really 20. So if I look at these two scenarios, this one has a bigger area than this one. So this guy is automatically out. But what's the perfect numbers in order to give me the biggest area? That's what we're trying to find. Okay. So what are the two formulas? I don't know what the two numbers are going to be. So my first one is going to be x plus y is going to equal to 30. And then what we're going to do is we need another equation. The other equation is going to be x times y. And this is my area. This is the area. And this one is the one that we're going to maximize because we found maximum. Now remember from calculus, in order for me to find maximums and minimums, I need to take the derivative. So I'm going to be doing the derivative of this equation. So this is the one that I want. But it has two letters. It has two variables. It has x and y's. And what I want is I want it in terms of one variable. So what I'm going to do is I'm going to solve for the letter y. So in this case, I'm going to take and I'm going to subtract an x from both sides, and I'm going to end up with y is going to equal to 30 minus x. So I'm going to take this now and I'm going to substitute it into this one. So I can now say that my area is going to be x times 30 minus x. If I distribute, I'm going to end up with 30x minus x squared. And this is my area in terms of one variable. So what I want to do now is I want to take the derivative because I want to find the maximum area. So I'm going to take the derivative of that. So that means that a prime is going to equal to 30 minus 2x. To get the critical points, we set it equal to 0. So that means instead of moving the 30 over, I'm going to move the 2x over. So 30 is going to equal to 2x. I divide by 2. I divide by 2. So that means that x is going to equal to 15. So what I have now is I have my x coordinate. My x coordinate is 15. So if I have 15 plus y is equal to 30, that means that y is going to be 30 minus 15, which is going to be 15. So that means that my two numbers is going to be x equals 15 and y is equal to 15. So what's 15 plus 15? That's 30. So what's 15 times 15? Well, 15 times 15 will be 225, I believe. Okay? 225. So that is going to be my maximum area. Now, if you notice 20 and 10, man, that was 200. That was really close. All right, so shall we try another one? In this scenario, we're trying to find a right cylinder can that has a volume of 1,000 centimeters cube. Find the dimensions of the can whose area uses the least material. So it wants a minimum area. Remember, max and mins are critical points. Okay, so I need to know a right cylinder can. So I'm gonna make a right cylinder can. Here's my right cylinder, and I know that my volume has to equal to 1,000. So this one has to have a volume of 1,000. So I'm gonna call this guy R, and I'm gonna call this guy H. So what's the volume? The volume of a cylinder. The volume is gonna be pi r squared times H. Okay. So let's continue reading our strategy here. It says read the problem, which I did. I drew a picture, which I did. Now there it says state the two formulas. Well, I'm kind of stuck here, and I'm saying, no way. My volume is going to be pi r squared times H. So that means that I can substitute that in here, and I can say 1,000 is going to equal to pi r squared H. And that's only one formula, and it's saying it's got to have two formulas. So then I go back and I read the problem again. It says design a right cylinder can that has a volume of 1,000 centimeters cube. Find the dimensions that uses the least area. Well, the least area, we're talking about surface area. That's what I needed. So the area of my can is going to be pi r squared times 2 pi r squared, right? Because there's two circles, the top and the bottom, and then plus 2 pi r h. And this right here is my lateral surface area, and this is my top and bottom. Okay, the top and bottom area. So now I have my two equations. So that means that what I'm going to do is I'm going to solve for my letter H. So in this scenario, H is going to be 1,000 over pi r squared. So I'm going to take this guy now, and I'm going to insert him in here. So that means that my area, in terms of one variable, my area is going to be 2 pi r squared plus 2 pi r h. But h now is 1,000 over pi r squared. So if I simplify that, I'm going to have 2 pi r squared, and the pi here is going to reduce, and here I'm going to end up with 2,000 over r. So now I'm going to take the derivative, and when I take the derivative, I'm going to end up with 4 pi r, right? And remember what I told you, memorize the derivative of 1 over x, and the derivative of 1 over x is negative 1 over x squared. So this is going to give me negative 2,000 over r squared, and I set it equal to 0. So I'm going to be solving this equation. So I'm going to move this guy over, which is going to give me 4 pi r is going to equal to 2,000 over r squared. I cross multiply, and I'm going to end up with 4 pi r cubed is going to equal to 2,000. I divided by 4 pi. I divided by 4 pi. So that means that r cubed is going to be the, I'm sorry, I took the cube root already, and I shouldn't have. It's going to be 500 over pi. So then what am I going to do now? I am going to take the cube root. I'm going to take the cube root of the left and the cube root of the right. That means that, oops, let me put a cube here. So that means that r is going to equal to the cube root of 500 over pi. And this is where we're going to have the minimum value. Now, how do I test it? Well, I have to actually make sure that it's concave up, and then it's going to give me a minimum. All right. Now, how do you find the height? Well, to find the height, remember, because you want the minimum area, so I'm going to take this r and I'm going to substitute it in here, and when I substitute it in there, I'm going to be able to solve for the height. So now I have the dimensions. I have my radius and my height, and that's going to conclude our optimization. All right.